Hi, good day. This is Jeremy Corporal, and today we are going to have a virtual lab, which is in the topic of orifice plate. Now we have here our aim is we are to design an orifice plate for typical applications. Now we have here four objectives. Now the last two will be doing this for the next session, but the first two will be doing this for this session. Now the first is to calculate the differential pressure developed across an orifice plate. Second is to study the effect of change in process fluid on the developed differential pressure. Now, if you ever wonder what is an orifice plate is a device, one of the most popular devices for the control or for the measurement or the control of the fluid flow. It is inserted in a straight line to run of smooth pipe to avoid disturbance of flow patterns from fitting and valves. Now, we have here the pre-test. We have 5 questions before we move to our simulator and our procedure. Now, the first question is the rate of the change of momentum is proportional to impressed force and takes place in direction of that force. That is A, second law of motion, B, a first law, C, third law. Now we know that the Newton's law has three law. We have the first law is the law of inertia. An object at rest remains at rest, and an object at motion remains in motion. Now for the second law, it is a law of acceleration, meaning that the force is proportional to its mass times acceleration. And the third law is the action-reaction, meaning that if you hit an object, it will hit you back with the equal force that you applied. Now, we know that since this is a moment proportional to the force and place of the direction, the law that governs the statement is the second law. Now, the Bernoulli's equation is obtained by integration of, it is the Euler's equation, since the continuity equation is also can be called the transport equation. So, the characteristic of flow like velocity, density at any point do not change with respect to time. So, if the velocity, pressure, density doesn't change with respect to time, so the flow is steady flow. Fourth question is for the flow through pipes, Reynolds number is less than 2000, the flow is called as. So we know that as the Reynolds number increases, the flow will be turbulent flow. So for Reynolds number less than 2000, the flow is laminar, and for the Reynolds number between 2000 to 4600, the flow is transitional. But for Reynolds number greater than 4600, the flow is turbulent, meaning that the flow has eddies. For the fifth question, we have the Reynolds number is given by formula rho dV over mu. Rho stands for the density of the fluid. Now V is the velocity of the fluid, and D, or the length, is the diameter of the fluid, and U is what we call the viscosity of the fluid. Now, the answer is letter B, and then click submit. And now, we now move to the simulator. Now, the procedures will be applied in the simulator. So we have here click for simulator. Now, our level 1 is we have our level 1. It is a measurement of differential pressure. We are going to calculate the differential pressure. So we have here first step is to study the diagram completely. So we have here this is our pipe, and the fluid flows on the pipe. Now we have here the orifice plate, which is inserted on the pipe. We have here the pipe threads as well as the nut used for give stability, as well as a stud. So we have here our beta. Beta stands for beta is the ratio of the orifice diameter to the pipe diameter. So we have here the orifice diameter. This is the orifice diameter, and to the pipe diameter, which is this one. So if you ever wonder the formula of our calculation, so here is the we have the D orifice diameter, the small diameter, and the big D is the pipe diameter. So we have here, click on the ratio of the orifice diameter to the pipe diameter. So we take, for example, our ratio is 0.4, and our and our and our diameter of the pipe is 25 millimeter. So as you can see, the pipe change. For example, we are going to select 25 diameter. So click the configure. So you have here the flange tops. Now here we are going to apply, we are going to measure or to control the feed rate or the volumetric flow rate. We are going to calculate the differential pressure. So for example, we have here, if our volumetric flow rate is 1568, and we then click the coefficient CD. So we are given with the coefficient, which is 0.611. We have here the formula. CD is coefficient of discharge. It is the ratio of the actual discharge to the theoretical discharge. So we are given with 0.6618. Now we are required to calculate the differential pressure. We have here the formula. So the formula for the differential pressure is this one. And if you're going to calculate the differential pressure with the given volumetric flow rate, as well as the for our volumetric flow rate, we have the 1568 liter per hour. So if you want to calculate, you can use this formula. QV, or the volumetric flow rate, is equal to this equation. So by calculation, we can have the value of 0.000214. Click submit if you already calculated the value, the differential pressure. So we'll be doing this for 3 times. For 4 times. So we now we're going to change the volumetric flow rate. We're not changing it, increasing the volumetric flow rate 1777. So if you're going to click, okay, 1777, then just click the green box to click our coefficient of discharge. So the new coefficient of discharge is 0.6113, and then our beta is constant 0.4. So we have the value of the next value, that is 1.3189 times 10 to the power of -3. So the value that I got is that is 0.10135. Submit. So the value that we got are correct. So again, we now change the volumetric flow rate, increasing the volumetric flow rate, and then click on the CD. Then we can now calculate the new differential pressure. So that is 1904, and then our 0.6111, then our C is constant. So that is 1.515 times 10 to the power of -3. 1.515. So the value that I got is 0.155. So submit, then the correct. So this will be I think this will be our last. So we increase the volumetric flow rate, and then we change the coefficient of discharge. So we have 2003, then 0.6109, then RC is constant, so that is 1.6, okay, shift 203 to 6 point, okay, 3.4, 1.678 times 10 to the power of negative 3. So the value that I got is that is 0.00171. So submit. Then we now unlock the level 2 as well as the plot as well as the next value. So let us now look on the plot. Let us click on the plot green box. Now as we can see here, we have here the plot of we have the volumetric flow rate on our abscissa, and we have the differential pressure on our ordinate. Now as we can see here, as we increase the volumetric flow rate, the differential pressure decreases, meaning that the pressure or the P2, since the differential pressure is P1 minus P2, meaning that the P2 decreases, or the pressure after the orifice decreases. Now let's move to the let's then click the level 2, since we unlock already the level 2, and we now select the, here in this level 2 we are going to select the kind of we are going to change the service on flow measurement. So for example, we are going to select the steam, so it changed into steam. So we now click the configure, yes. Now as we can see here, we have here the plot of we have the volumetric flow rate on our abscissa, and we have the differential pressure on our ordinate. Now move to the post test. So we have here the 5 questions. So we have the first question is, vena contracta is a point where velocity is maximum and static pressure is minimum. Second is, generally material used for the orifice plate is it is actually stainless steel, but since there is no stainless steel here, the second one is the phosphor bronze. So beta ratio is defined as, we know that beta ratio is the ratio of the orifice diameter to the pipe diameter. So letter A is the correct answer. Now for number 4, convert LPM or liter per minute to cubic meter per second. You have to multiply 1.667 times 10 to the power of negative 5. It can be of blank types. It can be of eccentric or concentric, so any of both. Submit. Now we now move on the last part of our virtual lab, which is the review questions. Now first question is, describe the construction and principle of working of an orifice meter. Now we know that orifice meter is a device used to measure the differential pressure of a pipe. Now the orifice plate, we know that it should be installed in a straight line or smooth pipe, and to avoid disturbance of flow patterns from fitting and valves. Now second question is, what are the different types of orifice plate? We have 4 types of orifice plate, which are the concentric orifice plate, we have the eccentric orifice plate, we have the segmented orifice plate, and the last one is the quadrant edge orifice plate, and it has different functions. The third question is, write a note on the advantage and disadvantage of orifice meter. Now we have one of the advantage of the orifice meter is that it measures wide range of flow. Second is that small plate and can be easily installed and removed. But one of our advantages, on the other hand, it requires homogeneous fluid to measure the difference of the pressure. Second, it requires single phase liquid. And the third one is that it causes pressure drop. The fourth question is that state and elaborate what kind of application the orifice meter is best choice. So the orifice meter is best choice for the water treatment plants, as well as in the natural gas industries, refineries, petrochemical plants. Fifth question is what are the design guidelines of orifice meter? So the design guidelines of orifice meter is that it has no fixed design guidelines, but it should not be reversed. That's the main purpose of the orifice meter. It should not be reversed, or else it will not measure the differential pressure. I think that would be all. Thank you for listening, and I hope that you've learned a lot in this channel. Thank you and God bless.